This is video lecture number 8, and in video lecture 7 we talked about these pre-experimental type research designs, including crude, simple correlational studies. Not all correlational studies should be considered pre-experimental though, even though some can be very crude and basic and are best considered pre-experimental. Some correlational studies are very sophisticated quasi-experiments. We're going to talk in greater detail about quasi-experiments later, what makes something a quasi-experiment. But in this video, I really want to talk about correlation in general and correlational studies. Correlational studies look at the relationship or concurrence of two variables on some dependent measure. So you measure two or sometimes more variables and see if, well, when variable 1 changes, does variable 2 change also? And if it does change, does it change in the same direction as variable 1 or in the opposite direction of variable 1? Of course, the answer might be that it doesn't change at all. So those three possibilities are known as positive correlation, negative correlation, or zero correlation. And this slide illustrates all of those in the context of cars. So on the left here, we have a negative correlation shown between automobile mileage and value. This makes sense. The more miles a car has on it, the lower the value of the car. In the center, we see just this crazy scatter plot here of these data points, and there's really zero correlation between automobile color and value. And then on the right, we have illustrated a positive correlation between the number of car accidents a person has and that person's insurance rates. Certainly, as a general matter, we know if you have more reported accidents, your insurance rates are going to go up. A classic example of positive correlation is between smoking and lung cancer. This correlation is seen both with time and quantity. So, for example, the more a person smokes and the longer a person smokes, the higher the risk of lung cancer. An interesting example of negative correlation in the legal arena is the relationship between age and committing violent crimes. Assuming, though, that you start measuring in the late teens, right? That makes sense. As we age, overall, we commit fewer crimes, but we do have to note that if we did include age from infancy on up, we'd get a very uneven shaped correlation, because obviously crime commission starts at 0 in infancy, doesn't really rise much until around the early teens, and then reaches a peak in the late teens or early 20s before going back down again. I'm sure you've all probably heard this truism in science that correlation doesn't imply causation. It's true that classically speaking, you can't automatically deduce a causal relationship between variables that are correlated. This is one of my favorite XKCD cartoons, so you should probably pause the video now and read it until you figure out why it's funny, and then go on. So the idea illustrated in the cartoon that you can't necessarily deduce a causal relationship even when you have correlation is true, because let's say you have a positive correlation between two things like we see here in our perfect 1.0 correlation. Well, this can either be because variable A rising causes variable B to rise, or it can be the other way around. Variable B can cause variable A to rise. But it could also be that some third variable x is actually causing both A and B to rise simultaneously, like our hot weather causing increases in ice cream consumption and hot weather causing increases in drowning example that we've already talked about. Tobacco companies always insisted on this point in critiquing smoking research. They tried to argue that, well, we just don't know for sure if smoking is a cause of lung cancer just because the data were there showing a strong correlation. And another example we already talked about is that if we have data that violent people watch more violent television than average people, we don't know which one might have caused the other or if there's any causation at all. Does watching violent TV lead to violent behavior, or does being violent in general lead people to seek out violent TV shows, or is there some third factor that causes both, like exposure to electromagnetic fields or being a psychopath who lacks normal emotional feelings, leading to both acting violently and choosing to watch violent television? Of course, all of these might be partially true. So this inability to imply causation from correlation can be overstated. It's not always a problem. We do have to remember that we're not always concerned with cause and effect relationships in science. Most of the time we are, but not always. So if you want to just make predictions, then directionality and third variables not always a problem as long as you have really solid data on the correlation. So in the example about violence and watching violent TV, if any of those possible causal paths are true, still knowing that a person watches a lot of violent TV does help you predict, at least to some extent, whether he or she will be violent. And the same thing with ice cream sales and drownings. So if you're making predictions using correlation, you want to know not only whether there's a positive or negative correlation between the populations on the specific measure, but you want to know what the strength of that relationship is, because a stronger correlation is going to give you more accurate predictive power. If you want to describe the correlation between two variables or two data sets, you use a mathematical formula to calculate the correlation coefficient. And the most commonly used value for correlation coefficient is the Pearson's product moment coefficient of correlation, known sometimes as the Pearson's R, right here on the slide, R. Here's the equation for that, which thankfully we don't have to understand, but the general things I want you to know about correlation coefficients are here on the slide. This correlation coefficient is a number that indicates the relationship between two or more variables or two or more data sets, and it's usually listed in research studies, again, as this letter R. Sometimes it's listed as P. And the value of the correlation coefficient is always going to range from a -1 here. That's a perfect negative correlation. To a +1, that's going to be a perfect positive correlation. So a perfect correlation of positive or -1 indicates that for every unit of increase or decrease in one variable, there's an increase or decrease in another variable by that same 1 unit. Here we see a graph of data points that form our perfectly straight line, showing our perfect 1.0 positive correlation. Here's a perfect negative 1.0 correlation. And here we see an example of a negative 0.3 correlation. So often when you see data illustrated with a correlation coefficient, you're going to see a diagram like this. It's called a scatter diagram, which shows all the actual data points that were obtained in the study. And the way you get from all of these data values to the actual number of negative 0.3, and the way you get to this angle here of the line on the graph is by using that mathematical formula where all of your individual data points are going to get factored into the correlation coefficient equation to give you your value of the coefficient. So nowadays this is going to be done completely automatically by a computer after data values are inputted. And looking at this scatter diagram, I think you can understand that a correlation of 0.3, whether it's a positive 0.3 or negative 0.3, that's considered to be a pretty low correlation, and you can understand. This is a great slide showing scatter diagrams for data ranging up here in the top left-hand corner, showing zero correlation, and then the correlation coefficient increases with each diagram. You can see the data points kind of organizing themselves, and then down here on the bottom right, we have close to an almost perfect 1.0 correlation. So it gives you a great sense of what the values between 0 and 1 mean in this context. I want to look at some real life examples. So here on this graph, we see a correlation scatter plot of height and weight in humans. So what do we see? We see there's a positive correlation, but not a perfect correlation. Obviously, there are many shorter people that might be on the heavier side, right? And we do have some taller people that can be on the skinnier side, the lighter side. So those outliers in our data actually end up affecting the correlation coefficient. An outlier in your data is going to reduce your correlation coefficient. Here we see another interesting scatter plot looking at fitness level and percentage of body fat. So what do we see? There's a negative correlation. The more fit you are, the lower your body fat percentage, and vice versa in general. And yet we see again that it is not a perfect correlation by any means. There are some people with low body fat who score low on this measure of fitness, and some with a high body fat percentage, say over here, that score pretty high in fitness. So that does pull our correlation down from a pure -1 correlation coefficient. Here's another one, a little bit depressing one, showing that as people age, the average height decreases. So age is slightly negatively correlated with height. And I've often wondered whether this particular diagram reflects the shrinking that happens as our cartilage breaks down and our spinal discs degenerate, or whether it might also include the fact that men generally die younger than women and are also taller, so that there is a higher percentage of women represented in the older ages reflected on this chart. I'm not sure about that, since I can't remember now where I got these correlation charts. But certainly, if this was a chart in a study, you'd have that information where these data points were obtained. Here's a data set for which you might calculate a correlation coefficient, but you can see that you don't have a neat linear relationship here. So your correlation coefficient is going to be lower than it would otherwise be. And it might not be a very good way to describe this particular data set on its own. This graph shows correlation between weight and fitness level. You can see that fitness is actually pretty low at the very bottom weight, and at first fitness increases with increasing weight before then going consistently down as you get over a certain weight level. This might reflect the fact that sometimes very thin people don't have much muscle mass. This could affect their fitness. So again, you may go ahead and calculate a correlation coefficient here, but you wouldn't want that to be the only way you described this very interesting data set. Here's another really interesting one. You have some fascinating data that can certainly tell you something, but your data doesn't fall in any kind of a linear arrangement. So correlation coefficient's not going to be a good statistic at all to use to describe this data set. In fact, your correlation coefficient here is going to be close to 0. But what the data here do tell us is that, well, test performance actually improves when someone has a certain amount of anxiety. Probably This is due to an adrenaline rush that might help with your focus and your speed. But as you see on the graph, anxiety above a certain level starts to negatively affect test performance. Probably all of us have had this experience before. On the other hand, just because data isn't perfectly clear doesn't mean correlation coefficient is meaningless. So here we see our class mascot, Abby, the wonder dog. Many of you probably know the generalization that 1 year of a dog's life is equivalent to about 7 human years. And this is reflected here in the graph on the left with a nice perfect linear shape. But the graph on the right is a more accurate depiction, showing that the ratio of human years to dog years is actually higher in the first couple of years of a dog's life. So you see in the first couple of years of a dog's life, the dog is actually aging probably faster than the equivalent of 7 years. And then it settles down into that rough 7-to-1 ratio. And then, in fact, later on in a dog's life, the ratio drops a little bit. So it's not actually a neat linear relationship, but a correlation coefficient, still going to be a meaningful statistic to describe a graph like this. Now, the other thing I want to point out is that outliers in your data can severely affect the correlation coefficient calculation. And the 3 images on this slide, I think, illustrate it very well. So here on the top left, we see that all but one of our data points here line up pretty well for a high correlation coefficient. But look at here, because of this one outlying data point, the mathematically calculated coefficient here is only around 0.2 to 0.3, depending upon what formula you use. In this top right image, this overall image here, you see a very dramatic effect of adding in here and taking out here your outlying data point. So without the outlier, we have a relatively high correlation coefficient of 0.7, but if we add this data point back in, our correlation coefficient gets dragged all the way down to 0.4. So one outlying data point, especially when you might only have 10 or 20 other data points, really is going to affect your calculation. And the bottom image here shows the effect of adding 2 different outliers. So starting on the left, we see data points here shown, giving us a correlation coefficient close to 0.9, so very good. In the middle here, we added this outlier to our data point. We see what happens now. It's pulled our correlation coefficient all the way down to 0.37. The last one, though, is really interesting. Here, we've also added an outlier up here, but our outlier that we added here falls roughly on the linear line of the other data points. And so we actually see this outlier increase our correlation coefficient all the way to 0.97. This slide shows a couple of examples of samples of students and their verbal SAT scores and their grade point averages. Okay, so what we have on the slide here is these charts, and each chart corresponds to the data that's graphed to the right of it. So our first example of student data here, this one, graphs out very nicely, showing this very high 0.94 correlation between our verbal SAT scores and the student GPAs. But down here, the first thing you should notice if you take a look at these is that our data here, they're all the same as the graph up above, aside from one student. So when we take this student here, Corbin, okay, and we change this value, we change his GPA from a 3.9 up here to a 2.2 down here. And we show that data point here in the graph. We see that he now is an outlier and his data point pulls our correlation coefficient all the way down to 0.32 or so. So again, with an outlier, the correlation coefficient, not a good statistic to really convey the import of our data. The last couple of slides are very interesting for law students because they have to do with correlation between various U.S. news variables and bar passage rate. So we see pretty high correlations here between peer assessment of law schools and lawyer and judge rankings and bar passage rate, 0.84 correlation coefficient. And our correlation coefficients, as you can see, are even higher when it comes to GPA and LSAT scores of students and bar passage rate overall at a particular school. On the bottom, we see our negative correlation here between percentage of students accepted, right, the selectiveness of a law school, and bar passage rate, and student-faculty ratio. So the more selective a school is, right, the lower the percentage of applicants it accepts, the higher the bar passage rate is going to be. So the more selective means a higher bar passage rate. And down here, student-faculty ratio, more professor attention seems to be associated with higher bar passage percentage. So if you have more faculty per student, that's a good factor for bar passage. And this last slide just shows a potential scatter plot diagram of the median LSAT scores from various schools and what their bar passage rate might look like that would get you to that 0.8 plus correlation coefficient. And this is the end of video lecture number 8.